Hey everybody, this is Mrs. Audiemeyer, and I was going to go over the 5 different types of chemical reactions with you guys today. Now, I know that you can look at the notes and you can kind of copy things down and you think you don't need to watch a video, but I feel like I've got some extra information that's going to be helpful for you with the lab that's going to be coming up and just some kind of stuff you would probably find useful when we talk about the different types of chemical reactions. So to kind of start off with, there are thousands and thousands of different types of chemical reactions that happen. And we can't specifically identify each type of reaction as fitting into one of the 5 types of chemical reactions that we're going to talk about. So there are tons of different categories, but when we're talking about kind of your basic introductory chemistry, there are 5 different types of chemical reactions that you see. And then if you want to get kind of further into it, if you get deeper into chemistry, there's more kind of categories that go with that. But in general, a lot of your basic chemical reactions can fit into 5 different categories, or one of 5 different categories, and sometimes you can get them into more than one of those 5 categories. So we're going to kind of go over those, and I'm going to give you some hints as to things to look for, things you could see in the lab potentially, and kind of how you would deal with those things. So hopefully you've taken your notes on these, and then you can use this video to kind of add to those. So the first type of reaction that we talk about usually is the synthesis reaction or combination. And synthesis means to put things together, and combination also means to put things together. So the general idea behind a synthesis reaction is that I take separate components, and those could be plain elements, they could be compounds, they could be a combination of compounds and plain elements, and you just need to take multiple things and combine them into one thing. So it could be 2 different reactants and then one product. It could be 4 reactants and one product. It just kind of depends on the specific reaction, but the way that you know them generally is that we have multiple things on our reactant side and then one thing on our product side. And so they combine together. Now, an example of this type of synthesis reaction is going to be the synthesis of salt, sodium chloride. So what happens is, in this case, the sodium is in its solid form and it's combining with chlorine gas. So if you think about that, that's like a chunk of sodium metal, and then chlorine gas is being added from, usually they like pipe it in, and then you end up getting solid sodium chloride. A lot of times in synthesis reactions, the mass goes up when you are thinking about your lab conditions. And now you say to yourself, well, Audiemeyer, you said we had law of conservation of mass, which is true. And the mass overall is conserved. But if we look at data in the lab, like if you look at a chunk of sodium and you put that on the balance, and then you add chlorine gas into it, the chlorine gas adding to it is going to raise the mass of the sodium chloride. So a lot of times in lab, it will look like mass was gained, and that's usually because we add a gas from some outside source to make that happen. So a lot of times in synthesis reactions, you'll see a mass increase in your actual lab conditions. Again, the total mass is conserved, but usually in a synthesis reaction that is coming in as a gas, and the gas mass isn't weighed beforehand so that it comes in, and a lot of times it's added. So we could find the difference between our starting mass of sodium and the solid sodium chloride, and that would be the mass of the Cl that was added to that. Type 2 is decomposition. Now, decomposition is the exact opposite of this. So if you think about synthesis as like, oh, hey, we're together and we're dating, the decomposition is the breakup of that. So a decomposition deals when you start with one chemical and then it turns into multiple separate chemicals as a product. So in this case, we have A and B stuck together, and then they turn into A plus B. Now, again, this could be chemicals in compound form or in elemental form. It just kind of depends. But the way you know it's decomposition is that we have things combined and then we have them broken up. And the example I have down here is the decomposition of calcium carbonate. So if you look here, the calcium carbonate breaks up into calcium oxide, and we start off with a solid here, so we'll have our solid, and it breaks up into solid calcium oxide and then gaseous carbon dioxide. So if you think about that, we have CO2 gas that's escaping. In that case, our mass of our solid will actually go down because the CO2 is leaving out. It doesn't happen in every decomposition, but if you have a decomposition reaction that produces a gas, your overall like reaction container, if it's not sealed, and in this situation you don't want it to be sealed because if we heat that up, it could explode, which would be not great. If you have the reaction open to the atmosphere, the CO2 is going to go out and escape and make your mass go down. Okay. Next one is a single replacement reaction. Now, a single replacement reaction is a little bit more of a specific set of circumstances compared to the synthesis and decomposition. In a single replacement reaction, you have one element and then a compound. So I have a plain element here, and the element could be in its monatomic form, which means it's just one atom, or remember that there are some elements that have diatomic properties like hydrogen, oxygen, nitrogen, those kinds of things. There are 7 of those. So what happens in a single replacement reaction is that you have one element all by itself and then a compound. And in our example here, we have zinc as the element by itself, and then HCl is our compound. So I'm taking solid zinc and I'm putting it into aqueous HCl. What's going to happen is, in this case, the zinc and the hydrogen are going to switch positions. So the hydrogen gas now becomes an element by itself, and then the zinc partners up with the Cl in this combination. So in our example with the letters, A and BC get together, and then we have AC as our combination and B. Now, the way that the single replacement happens, it's not always that the first element switches in the compound. It depends on the type of oxidation number you have. So if your element makes a positive oxidation number, it's going to switch with the cation in the compound. And if your element makes a negative oxidation number, it's going to switch with the anion in the compound. So it kind of depends, but the way that we recognize it is that we have an element by itself and a compound, and it makes a new compound with a different element on its own. In this case, we'd have aqueous zinc chloride. So if you can imagine that, it's a solution. We've got some water in there. The zinc ions are floating around in there. The chlorine ions are floating around in there. And then hydrogen gas is bubbling out of this particular one. Okay. The next one is a double replacement reaction. And double replacement reactions show up in one of 2 ways. One, they show up as a precipitation reaction, and we've talked about these before. Precipitation reactions form solids at the bottom when you mix 2 aqueous solutions together. The other way you see a double replacement reaction is in an acid-base neutralization reaction, and if you put together an acid and a base, they make water and a salt, and that's a type of double replacement reaction. So the way a double replacement reaction works is that instead of like a single replacement reaction, you have a single element doing the swapity-do, it is 2 elements doing the swapity-do. So in this case, A and B are together, and then it's C and D. And what happens is A and C switch spots. So if you think about it, like the cations switch who they're with. It's kind of like if you're dancing with somebody and your neighbor is dancing with somebody, and then you switch partners. That's a double replacement. So in the case of our example here, I've got potassium and chlorine as partners in my reactants, and silver and the nitrate ion. And then in the double replacement, now the potassium and the nitrate go together, and the silver and the chlorine go together. Okay. Now, if we look at this reaction and we look at the phases, we go aqueous, aqueous for our reactants. So I have 2 aqueous things put together, and they make aqueous KNO3, potassium nitrate, and then they make solid AgCl. So that means that this is going to be a precipitation reaction. So this is one of those scenarios where you mix 2 clear solutions together. When you mix them, they turn into a precipitate that settles out at the bottom, and then solution up top. So if we'd be looking at this, the KNO3 would be ions up at the top, and then the silver chloride would be settled down as solid at the bottom. And you could separate those if you needed to look at one versus the other. Okay. And the last type is combustion. Now, there are kind of 2 types of combustion reactions that we see. There are the type with a hydrocarbon, and a hydrocarbon is something that's got carbon and hydrogen in its formula, and usually that's it. Once in a while, you'll see a carbon, a hydrogen, and an oxygen, but that's pretty much all you see. And then here's where it's very strict. So it's just that hydrocarbon plus O2 gas, because you're going to feed in oxygen gas, and they always make carbon dioxide and water, and usually some heat because it is a combustion reaction. So the only two products in theory in a combustion reaction, when we're talking about the combustion of a hydrocarbon, is going to be carbon dioxide and water and some energy, some heat. Sometimes you get some flame, that kind of stuff. There is another type of combustion reaction that happens, though, when you have just a plain element. And it's kind of like a synthesis reaction as well. If you look at this first equation here, if I have carbon and then I combust it with oxygen, I make carbon dioxide. And you do see that as well. So when we talk about combustion, usually it's the addition of oxygen into something. So it's either going to be oxygen and an element turning into that element oxide, or your hydrocarbon plus O2 and then CO2 and H2O. And when you have a combustion reaction with a hydrocarbon, a lot of times you do get weird things that are not supposed to be made, and those are caused by something called a side reaction. So what can happen is, in a process of combustion, it'll undergo what they call incomplete combustion, so it does not combust all the way. And then when that happens, you get kind of side products like carbon monoxide and things like that forming, which are, not great always. So just some things to be aware of. But with combustion, you're either going to see an element and oxygen together to make that oxide, or the hydrocarbon and oxygen. And if that's the case, they always make CO2 and H2O, and that's it. So like if we're asking you to write the equation for something, it's just CO2 and H2O and then some fire or some heat or whatever. Okay, so those are your 5 types. After you get the hang of identifying the 5 types of reactions, we're going to be doing some different lab experiments where you're going to be going through, taking a look at the actual lab procedure, figuring out what type of reaction they are, and then answering a bunch of questions about everything that we have learned so far this year. And you're totally going to be ready for it. So if you have any questions, please make sure you talk to us in the meet. Otherwise, good luck.